Hello, I'll be introducing the project for estimating trajectory duration of industrial robot arm with machine learning. So this is a typical industrial robot arm, 6 degrees of freedom. Here's the controller box for it, and inside the controller box is a well-programmed machine that will generate a high-speed trajectory for the robot arms that's mostly optimized for like the quickest motion. These motions are usually time optimized trajectory, and they are highly dependent on the dynamic equations. So here's a quick example of such equation. As you can see, the equation is very complex for just a 2-joint robot, and for such a robot like 6-joint that's typically used, this equation will be very, very complicated. And this is the time optimized trajectory generation, the common illustration for it. You can see it's very nonlinear, and it depends on the upper and lower limits of the dynamic model, which means the overall trajectory generated by these industrial robot arms are very complex and basically not possible to reverse engineer and hand calculate a trajectory duration out of the start and end location. However, it is worth to mention that these math are deterministic if all the parameters are known. Of course, companies don't publish them. However, because they're deterministic, any given start location and end location will yield the exact same trajectory and thus the same trajectory duration. So about this project, the data are from the real robots provided by an anonymous company, organized and cleaned before using in this project. Project used the PyTorch for machine learning, as it is a quick and easy way to utilize GPU to accelerate the process. There are 12 inputs, as mentioned before. The start and end configuration of the robot arm, so 6 joint value for the start configuration, 6 joint value for the end configuration. Those defines the same trajectory basically all over different like iterations. The output will be one. It's like a time measurement of the trajectory, so how long the robot it take for the robot to execute such movement. We're using mean absolute error to measure the output, as this is less biased towards outlier or larger values. We're using 10H and ReLU later on as activation functions. So the first model being tried here is a linear only model. Of course, this is basically linear regression, so it quickly become obvious that it is not usable to fit such a complicated model with lots of cosine, sines, and some non-linear features here. Next thing we tried is adding 10H. 10H is a great activation features for such a regression problem. Basically, every other layer in between the linear layers, there's a extra 10H added in the middle. This model quickly approached a result of usable outcome. Now, this is a different one I tried with ReLU at the end. So the difference between the two models is at the last layer for activation layer, I switched from 10H into a ReLU. Now, the reason this works, I believe, is because ReLU is a sort of a clipping activation. So it clip all the value that's negative. And for our output, the output is a time measurement, which is always positive in value. Thus, the ReLU should fit very well with the actual model of the trajectory. This is a very strange model I found that works very well. It's mixing in one layer of leaky ReLU in the middle. Everything else is exactly the same as before, just this one extra leaky ReLU here. Now, as a result, let's see. These are two output of two different runs. They basically illustrate the same sort of outcome. So I'll just talk about with this graph. The difference between the two graphs are mostly from different initial conditions. So basically, we can see the simple linear network just doesn't work. For the leaky ReLU, it somehow can start converge early and then it approach a smaller arrow compared to the other, and it was able to maintain such a small arrow. As we can see here, this is also sort of true in the other case. Now, all of these other models, 10H or mixed with 10H ReLU, or even more complicated, longer models, all work. Basically, we able to reach a rough output error of 0.1718 absolute error. So as a conclusion, we can say this: the machine learning approach can certainly generate useful prediction for the duration of a motion, and depending on the scope of the engineering problem, this could be very useful, or this could be just a good guideline for what the value could be. In the future, of course, this project is very short and have lots of issues to be fixed. In the future, we would like to use a larger data set with more complex models. Right now, there's only about 6,000 data points, so not really enough for a deeper network stack or a wider amount of nodes. We would also like to add feature transform to the input in the future. In this round, I've tried some very basic feature transform, like normalizing the values and all that. Doesn't seem to help at all. In the future, we like to have more data, experiment with more complicated scenarios, see if we can get the error to even smaller, and thus make it actually very useful to predict a complicated, well-engineered industrial robot arm. Thank you.